Hi, Met330 people. So when last we met, we talked a little bit about probability. Now, some of you may already know what probability is, but so it won't hurt you to review it a little bit. And remember that we're talking about probability in the context of sources of random error. So remember, so far we've started talking about error in measurements as being either systematic or random. So remember that systematic error was the kind of error that happens all the time. It's deterministic, it obeys patterns, and it's somewhat predictable, and we can take strategies to avoid it. Random error, well, you can take strategies to minimize it, but the one thing you can't do is predict it. It's random. It's not predictable by its nature. And so this is one form of this is noise, right? Noise has causes, but when you look at a signal, it's just way too complicated to make any sense out of it. And it's corruption. It's corrupting our signal. It's corrupting the thing we want, right? So we've started to talk about probability as a means to quantify that and a means to describe that particular kind of error, random error. So if you remember, we introduced the idea of probability notation. So P, the probability of a condition. Right? So we said that the probability of a condition was if I repeated an experiment over and over and over and over and over and over and over again, if I did it many, many times, out of all of those experiments, what fraction of them would this condition be true? Right, so that's the idea. So we can have many samples, and some percentage of them will be true. So obviously the largest probability you can have is 1, or 100%, and the lowest probability you can have is 0. So if you get a probability of 2, you know you've done something wrong. Right, so that's the idea of probability, of course. And we showed a really simple example for a die roll. So what was the probability that x was less than or equal to 3? And we looked at different probability distributions for die rolls, right? So we had 1, 2, 3, 4, 5, 6, the 6 sides of a 6-sided die. And we showed that, well, these don't have to all be the same. You might have a weighted die. You could have all sorts of different individual probabilities. So you could have all sorts of individual probabilities. Let's not assume that the die is perfectly fair. If that's true, then this statement right here is evaluated by summing up all of the individual probabilities in my condition that I'm looking for. That would evaluate to true for my condition, right? Now, this was for a die roll, which has inherently discrete outcomes. There are only 6 possible outcomes. But for a measurement, this is what we said last time, for a measurement, though, we have infinitely many possible outcomes because it's a continuous measurement. How long is a blade of grass? How tall am I? What is the pressure in a pipe? Well, there are infinitely many answers to these questions. And so you can't sum up the individual ones. We can, however, integrate, right? So it's no longer summation, we move into the world of integration. So here we say that the probability that x is less than, I don't know, 3, for example, just to say the same thing, is the integral from negative infinity to 3 of the probability density function, x dx. Right? And so you might have some, and if this were 3, basically we're going to sum up the area now. Instead of summing up the heights of every point, we're going to sum up the area under a continuous curve. And that area will give us probability. Now, the critical question is, of course, what's the, and I'm using a lowercase p here, so lowercase p. What is the probability? What is the probability density function, little p? What is that, and how do we know it? Now, last time we introduced the normal distribution. Then the normal distribution we learned was, this is a little p, was 1 over standard deviation, square root of 2 pi, that's on x, times, now this is going to feel a little weird, okay. So this was the normal distribution. Now this feels just bizarre. It's going to get simpler in a little while. But remember, so there were two metrics, there were two parameters that completely define the shape of this curve. And it defines this shape, right? So one of them is the mean, right? Or the expected value, and that's the center of the entire thing. The other one is the standard deviation, right? Or the variance would be its square, right? And that's how spread out is it? Is it really, really confined and peaky? So that is, if we know x very well, for example, then this curve would be a narrow peak, barely permitting any deviation. The occurrence of a measurement far from the center would be incredibly improbable if we know x well, right? But what I've drawn here, well, this doesn't look like we know x very well at all, do we? Occurrences out here seem pretty likely, as a matter of fact. So, we introduced this idea. Now, and so there was one really important conclusion. These are neat ideas. These are important. We're going to build on them. But one of the biggest ideas that we developed last time was that if I ask the question, what is the probability that x will be exactly 3? In this system, we know that answer. It has a definite answer. There is a finite probability of a die roll being 3. In this system, in a continuous system where there are infinitely many possibilities, there is 0 probability, none whatsoever, that you will get precisely any single result. In order to have a finite probability in a continuous system, that is, in a world where any answer is possible, and where a continuum of answers exist, you need a range, a maximum and a minimum, in order to have a finite probability, in order to have a finite area. If I specify an infinitely thin area that is precisely one number, you get an infinitely small probability. That's the end of the story. Right? And this is a really interesting idea, right? So if you really follow that to where it takes you, if you really wrap your head around that, it's actually deeply disconcerting, right? To many of us who lived our lives in high school imagining measurements as, well, that's the answer. You put a ruler next to it, you read the ruler, you now know how long the thing is, right? To sever ourselves from that idea and start to imagine every measurement, without exception, as having these errors, these sources of error that create uncertainty, that create windows. No, the measurement is in a window. It's not a precise value. It's somewhere in here. This is a disconcerting idea. But the best theory available is that no, it's not like that. There's a window in which the measurement actually exists. This actually seems to describe the way measurements work pretty darn well. This window idea, right? Now, for example, just to take that a little further, if I take a ruler and I put it on, say, a piece of string, and I say how long is the piece of string, and I could report a number, 1 inch and 5/16, let's say. So 1 inch and 5/16, relatively short piece of string. The string is not precisely 1 inch and 5/16. If I counted atoms, for example, how many atoms long is the piece of string, you'd get a different answer every time you did it, depending on how you lined the atoms up, for example. But the answers would come in some window, right? When you get down to that level of precision, it matters what the temperature in the room is. It matters how hard you're tugging on the piece of string. It matters how straight it is when I lay it down to measure it, right? There are all sorts of sources of variability in the measurement all of a sudden, and the measurement would stop looking like a constant narrow peak, and as you zoom in on it, you realize it has some width, it has some uncertainty to it. There is some width to this probability distribution. We would get variable answers. The only reason with the ruler, the only reason that the answer would come back looking consistent is because your measurement is so crude you can't see that variability. You have rounded it away. And so, this is the way we choose in this class. This is the way we're going to choose to look at measurements, but you're going to find that this is consistent with the way that the elites in the world of measurement work, right? So the national governing bodies and the international governing bodies, right? This is all the way they approach the concept of calibration and in measurement theory, right? Okay, so we're going to keep going with this. So fundamentally, the problem that we have here is if I, let's set aside for a moment how do I know sigma and how do I know x bar here. Let's set that aside for just a moment. Let's pretend I have characterized my measurements pretty well and I know this distribution. Fundamentally, the problem may be, so how do I calculate the probability that if I measure a thing, let's say the length of a piece of string, what is the probability that my next measurement, instead of being 1 inch and 5/16, is 1 1/4 inches? What is the probability that or shorter, let's say, yeah, or shorter, let's say. That would be analogous to this problem here. Evaluate the integral from, in that case, it would be from 0 to, because probability shorter is 0. But anyway, yeah, evaluate the integral of this probability function for that length of string, that measurement function, all the way up to 3. Well, you could reasonably ask, all right, well, what's so special about the normal distribution? Why am I allowed to use that? Why should the length of string obey this particular probability distribution? Well, there's an idea, we're not going to go into it, and in any event, my expertise isn't statistics, but there's an idea called the central limit theorem, which is a really cool idea. You can Google it. There's a great Wikipedia article on it, and there's the idea is that if I take a whole bunch of random sources, right? So imagine every molecule in that piece of string all lining up, and each one has a little variability to its location. No matter what probability distribution each source of error obeys, they could obey whatever they want, whatever weird probability distribution they want. They don't have to be normal. But if I sum them all up, their sum does obey the normal distribution. This is a deeply counterintuitive idea, but sure enough, it works, and it's pretty darn powerful. And so and we use this in physics and engineering all the time. We basically, when we don't know any better, we basically throw the normal distribution at the problem and assume it works, and most of the time it actually does. So that's why we use the normal distribution. That's all I'll say about it. But so there's a deeper rabbit hole to go into there, but that's all we need. Okay, so that's a justification for why spending our time on this is worth it. That's why it even matters. Okay, so let's go deeper. So fundamentally, in order to start thinking about this, we need to be able to test that. I'm going to call it XA, right? So oh no, excuse me, I've already used XA for other things. Let's use X1. I was using X1 for that before anyway. Let's evaluate this integral right. Oh, excuse me, negative infinity. Okay, there we go. Wow, really struggling here. There we go. This integral right here. I need to be able to evaluate this integral somehow. So there we go. So this is not a very easy function to integrate. Not at all. The good news is that there are tables to do it. Certainly the very first thing we might want to do is do a change of base or a change of variable here, right? So if you and I were going to try to integrate this, let me emphasize, it's not trivial. It takes a bit of effort. But if we were going to attempt to do that, we would certainly need to do a change of variable here, because this is just messy. The very first thing we would do is say, well, we'll create a new variable. Let z equal this mess. Right? And then that should be much better, right? So that now the probability of z now here's the thing. We can't just substitute in. We can do this, that's fine. But we can't just substitute straight in for z and be done with it. Let's explore why for just a little minute. This is going to be helpful. The answer to why that gets messy is buried in units, believe it or not. So what are the units? What are the units on the probability distribution function PDF? Probability distribution function, not portable document format. What are the units on P? Well, I don't know, but, well, I do know, but we don't know yet. We haven't said yet. But what we do know the units on capital P. This is dimensionless. Capital P, right, was the probability, it's the number of occurrences out of all the tests I did, right? So this is a fraction. This is a dimensionless number. And, well, since capital P is an integral of little p times dx, right? Oh, wait a minute, what are the units on x? X is whatever my measurement is. So if x were in inches in my string example, right, then little p would need to be in probability per inch. So it's probability of x one is in units of 1 over x. Whatever x is. So if x were meters, then the probability density function would be probability per meter. If x were in psi, it would be probability per psi. And the reason for that, remember, the reason for that is it's answering the question. Little p is answering the question. If I widen this area just a little bit per distance along this x-axis, right? How much extra probability do I gain? It's asking the question, how much more probability do I pick up if I widen my window just a little more, right? So you can think of it as kind of a rate, right? And that actually works pretty darn well. So the reason that P of, I can't just substitute in, I can't just jam in a relationship for Z here and expect everything to work out is units. Look at the definition of P. Sigma, right, the standard deviation has the same units as x, right? So sure enough, probability here has the units of 1 over x. Absolutely, that works out. You might be tempted to just say then P of z is equal to, oh, we'll just substitute in z, no problem. So this was an intelligent choice. We're going to stand by that. But here's the problem that comes up if we're not careful. Nope. That doesn't work anymore. This probability per z is a dimensionless number now. Look at that. Z is dimensionless because x minus x still has units of x. So that could be in inches, let's say. So that's how many inches am I from my expected value of x, or my mean. And then I divide by the variance, or the standard deviation, which non-dimensionalizes it. So this is asking how many standard deviations am I away from my mean. So how many standard deviations have I moved away from my mean here? Well, so that's great and all, except that means the probability of z is not equal to this because the units don't work out. The explanation for what makes this all okay comes back with the integral. The capital P, z is less than z1, will be equal to capital P, x is less than x1. That is absolutely valid. That is correct. Because the units work out, everything's fine, it's a direct substitution, there's no issue. Remember, capital P is the original definition. That's the same number from which all of this other stuff is derived. So we can't just jam into the integral and hope for the best. And this was equal to so in other words, what we forgot about is the dx. We have to, if we're going to do a substitution, then we need to substitute for everything. So dz is going to be equal to 1 over sigma dx. Right? If I just differentiate both sides, this is a constant, this is a constant. There we go. Everything's good. So let's see how that works out. That means the probability that z is less than z1 is equal to, let's see how that works out. So by the way, z1, yeah, just substitute in x1 here, and that calculates z1, no problem. Yeah, let's see how this works out. So it was 1 over sigma x square root of 2 pi e to the negative 1/2. So I'm just rewriting this. It's dx. All right, well, dx over sigma x, sure enough, there's a sigma x right here. So I can just get rid of this and get rid of this and complete my change of variable here, or change of integration, change of boundaries here. That is much nicer. And so we find that the probability of z is in fact equal to the sigma goes away, which is exactly what we wanted to have happen. That's lovely. Now the reason for the 1 over the square root of 2 pi here is just to enforce that when we integrate this from negative infinity to infinity, we got to get 1, right? The probability that z is a number is 1. The same is true for x, right? So this coefficient here is just to ensure that that happens. It's to rescale everything. Otherwise, we would get rid of it and just deal with this. So that coefficient is just to make sure that the scaling all works out. Okay. So that's much easier. In fact, look at this. There are no parameters left. We've gotten rid of the mean. We've gotten rid of the standard deviation. And now, no matter what sensor I'm looking at, no matter what random process I'm talking about, I have one distribution that I can use for everything. So in other words, a problem, or we can now start to say, all right, so given All right, so if I'm monitoring a noisy signal, the idea is it's a voltage. So I'm calling my variable V now. So if I'm looking at a noisy signal and I've given you a standard deviation and a mean, right, we can ask, what is the probability what's the probability that the next measurement, right, so if I just take one more measurement, what's the probability that I get a number less than 4.8 volts? This is a well-formed question. If it feels a little abstract, right, if it feels a little strange and yeah, whatever, non-physical, imagine this scenario. Imagine I'm in a production environment and I'm monitoring a temperature signal and I'm a controller and I know if that temperature ever dips below a critical value, I've got to shut this process down because that's bad. That's going to harm the product. This happens, right? So if you have a noisy signal coming into a controller and you configure that controller to trigger a safety action if a signal ever drops below some threshold, it's worth your trouble to look into the probability that you get a false positive or a false alarm, right? So that noise just makes it appear that the signal has momentarily dipped below a threshold when in reality everything's fine, right? So this is not that non-physical. This is pretty real, actually. All right, so we can do this. To set it up, what we want is the probability that the voltage is less than 4.8 volts, and we can know that that's going to be this integral here from negative infinity to 4.8 volts, and that's the probability distribution function for V, right? dV, right? And so this has units of per volt, right? But dV has units of volts, and everything works out. So okay, there we go. This is pretty good. And the good news is normally we would have to calculate this integral. We're going to use tables. So you just look it up. Don't even bother calculating that integral. The truth is it's too hard. So this is not practical. So yeah, let's actually write it out once. We'll never write it out again because it'll be the same every time. But let me actually show what's happening here. So in other words, the probability of V though is just equal to 1 over, well, the standard deviation for V was 1/10 of a volt, we said. So standard deviation of V is square root of 2 pi. Or this is also true. So that was 5. There we go. So you can even plug in numbers, and you're going to get a probability distribution that looks something like this. So way out here at 5 volts, you're going to see something that right, so I call this a relatively noisy signal because we can stray fairly far from 5 volts and still see substantial probability of getting a signal. So we've asked what is the probability that 4.8 volts or less. So we need to evaluate the area here, right? What's the probability that I get a false alarm that my process is doomed when in reality it's fine? So this is a v. So all of this, and this is the horizontal axis here is v. So all of these are physical units. This is my physical problem, and this is how the probability of an event diffuses out as I get farther and farther away from my expected value, the central value here. So what we do, though, is, because this is hard, right, this is very hard, is we transform the problem into z and say, well, no, we're not gonna do work in volt units. That's crazy. Let's work in z units, which is unitless. We'll say, all right, what is my voltage minus my expected value or my mean, and divide it by my standard deviation. So in this case, Z1, I'm going to call it Z1, is equal to, I'm going to call it 4.8 minus 5 divided by 0.1. Now this actually has some pretty interesting interpretation if you choose to think about it that way. That's negative 0.2 divided by 0.1, or just negative 2. And that's dimensionless. This is volts per volt, right? All the volts cancel, everything's in volts. This just becomes dimensionless, right? So your negative, the number isn't, Z1 is in fact negative 2. So this is kind of interesting, actually. What does Z tell you? So we first introduced the concept of Z as, all right, this integral is hard, I don't want to do it. Let's do a change of a variable here to make it easier. And boy, did it. It simplified the problem rather nicely. Z actually has some pretty meaningful meaning, though, or it's a meaningful interpretation, though. It asks the question, how many standard deviations am I away from my mean? I've said that once before. I want to explain it a little more clearly here. So if I'm sitting right on top of my norm, or my expected value, my mean, then I am 0 standard deviations away from the mean. So Z would measure to 0. But if I have, and from there it deals in multiples of 0.1, right, in this case. So multiples of my standard deviation. As I move, I am 0.2 volts away from my mean. And if you normalize by the standard deviation, that means I am 2 standard deviations away to the low side. So I'm negative 2 standard deviations away. So the cool thing about that is Z will you can get any bizarre old shape of this curve you want for different physical processes. The units can vary, but once you're in Z units, negative 2 is negative 2 is negative 2. You can compare any two systems you want with weird units, and they will come out with having comparable shape. So that is very handy. Okay, so now let's figure out how we're actually going to evaluate. So let's finish translating the problem into the integral, and then we'll figure out how are we going to evaluate this integral. So the probability that voltage was less than 4.8 volts was equal to the integral from negative infinity to 4.8 times the probability of v dv, which is equal to negative infinity to negative 2 probability of z dz. And we know that because we figured out that in z coordinates 4.8 is the same thing as negative 2. So now we just need to figure out how to evaluate this integral right here. And just to prove I'm not cheating, remember, we said we did just the basic calculus, the change of integration, change of bounds on integration, right here, and this is what we got for the probability of z. Okay, now stop for a minute. So this is the problem we now need to solve. How do I evaluate that integral? So here we are. So this is our Canvas site. So when I come down to error, you'll see there's a lot of stuff here. There's extra materials. There's a textbook there. Okay, golly gee, we're not going to use it much. So there are there's what I really want to focus on is this older handout for error, and so these have older course notes, and at the end of them, so here they are. Click, golly gee, there it is. So there's a whole bunch of stuff, and it talks about stuff that we haven't talked about yet that we will get to, and some other stuff that we have. But ultimately, where we're going is, oh look, this is exactly what we're talking about right now. It's this stuff right here. And then at the end of it is this handy dandy table. All right, now let me go ahead and then go to click as a separate screenshot. Here I've got a full-sized version of that table. Zoom out just let me expand that. There we go. Lovely. So what we've got here is tabulated values, and if you look, this is exactly, I mean, they are using beta instead of z under the integral, but it's the same thing. Why they're even using z1. And look, it's exactly what we said. They're, for some reason, using a prime. I don't know why they feel like they need to use a prime. And so what's tabulated here, if for those of you who have seen z tables before, usually it's tabulated the way I formulated this integral, which is from negative infinity to a number, right? But our table for some reason is formulated from 0 to a positive value of z, and that's just what we've got. So let's look at it and try to make sense of this for a minute. So what we've got are tabulated values for different values, positive values, mind you, of z. And what is tabulated in the body of the table is the area underneath this curve right here. So in other words, to evaluate the probability that z were, let's see, that z were, let me show you, sorry, let me get it back on my camera. So for example, let's take an aside, we're going to come back to this. What's the probability that z is between 0 and, I don't know, 1.43, let's say. What's the probability that z is in that range right there? Well, let's find out. So that's what our table is formulated to do. We will figure out how to use it to calculate this in just a moment. So now let's go back to the table. All right, so to calculate the probability that z is from 0 to 1.43, I come up here and I look at, all right, these are my z values. I need to look up 1.43. Right? So the first two significant figures of z are listed on the left-hand column, and the third significant figure is in the horizontal column. That's just to make more efficient use of the page. So 1.43. So the probability that z is between 0 and 1.43 is 0.42, move my mouse out of the way, 4236. So I would write that like this. And that's just from the z table. All right. Now, here's an interesting question. What's the probability then that z is from negative 1.43 to positive 1.43? That's not in my table, but I bet we can figure it out. What is it going to be? 7. No calculator needed. You just double it, right? What we're taking advantage of here is the fact that the z curve is symmetrical, right? So the area on this side is going to be equal to the area on this side. So no problem. If you want to make symmetrical boundaries, right, so plus or minus a range, you just take half of it and double it. Easy. No problem. Neat. Okay, so that's done. Well, we can get really weird with it. Probability that z is negative 0.5, let's say. Let's have a little fun. all the way up to, I know some of you just are dying for me to use the number 7. I have to use the number 7. So we will say 0.77. There, are you happy? I haven't used a 7 in ages, so now you can be happy. Take your blood money. All right, so to do this, there's nothing here that lets me do that, right? There's nothing here that just tells me that answer. So what I have to do is get a little more clever than that. Instead, well, that's equal to the probability that z is, I can break it into pieces. Right? So I can do that, right? I can split probability into 2 parts. How do I know I can do that? Because it's just an integral, right? It's the integral of p of z dz from negative 0.5 to 0.77. Good thing I paid attention in calculus. So fortunately, because I paid attention in calculus, that reading this table is going to be easy. Right? Yeah, so you can just break it into 2 parts like this. Well, so all of these statements, this statement is the same as this statement is the same as this statement. But here's the and so we still have this problem though. I do not know what my negative bound here. There's no part of this table that allows me to go from 0 to a negative range in z. But we just established the area from here to negative 0.5 is the same as from here to positive 0.5. So in other words, this is no trouble at all. I can just do this. This is a little weird, but it works. There we go. So we do, so I've done 2 transformations. So I've taken this really weird lopsided bound, negative 0.5 to plus 0.77, right? So it's this lopsided interval under the probability distribution. I've looked at my table and said, well, I don't have anything like that in my table, but what I do have is positive numbers with respect to 0. So I split it into 2 halves, 1 half from 0 to 0.77. Okay, I can take care of that right away. I can just look that up in the table. This other half, this negative half, I don't know how to deal with that. Wait, yes I do. I could just flip it and make it positive and look it up again, and I can construct my probability from there. So I can do that, no problem. So in I go, I come in here and I look for, all right, so first I need the probability from 0 to 0.5 to 0.5. That's just here, 0.50. So that's in this first column here, 0.50. So that is 1915, 0.1915. All right, and then I need the I'm actually writing that down is the reason I'm saying it out loud. And then I need the probability that z is from 0 to 0.77, so I come down here to 0.7. Don't try to read 7.7, it's 0.77, so 0.772794, there it is. 0.2794. And so that results in, let me show you my paper again. Click. Oops, I think maybe that whole time you weren't seeing the table. All right, let me do that one more time to make sure you got it. So that's some camera mismanagement there. Sorry about that. So to get the 1915, I needed to read the probability that z is between 0 and 0.5. So I just look up 0.5. And 0.50, right? And that's 0.1915. It's right here. And then to look up the probability that z is from 0 to 0.77, I just come here and construct 0.77. So this row and this column. So z is 0.772794. There we go. All right, now I just need to add those two. No problem. All right. 907. All right, there we go. So there's my probability. About 47.1%. All right, so now that we've got some practice with the z-table, let's go back to our original problem. How do I determine the probability that this voltage is less than 0.48? Well, I don't have anything that allows me to construct that part of the curve, right? I need to go from here all the way to negative infinity. Negative infinity does not appear on this table. There is no way for me to do that. So I'm going to have to get really clever. Well, to do that, I need to use a couple of ideas. All right, let's rewrite that. So the probability then that V is less than 4.8 volts is equal to the probability that Z is less than -2 is what we said. Okay. Well, we're going to have to use some ideas. So the probability that Z is less than -2, I don't know what that is, but I do know this. The probability that Z is less than -2 plus the probability that Z is greater than -2 it must, right? By the way, you can add the or equal to or not. It doesn't matter. The probability that Z is exactly -2 is 0, so who cares? It doesn't matter if you include it or not. So the probability that Z is less than 2 plus the probability that Z is greater than 2 must sum up to be 1, because the probability that Z is a number is 1. It's going to be a number, you just don't know which one. Right? So, well, we can already say, all right, I don't know how to calculate this, but I can calculate this. So in other words, let's draw a quick sketch. Z little p. There we go. So I don't know what this is. But if I could figure out how to construct what this is, this area out here, I can use that to all I have to do is take 1 and subtract it by that. Well, what's this? What's the probability that Z is positive? 50%. Even odds. You're on one side or the other, right? So I know what that is. Neat. So now all I need to know is what this is. So the probability that Z is less than -2 is equal to 1 minus, now I'm going to construct this, 0.5, 50% plus the probability that Z is between 0 and 2. This I can look up. Click. The probability that Z is from 0 to 2. Okay, so I want to look up the probability that Z is at 2, that from 0 to 2. 2.0. So there we go, 0.4772. Click. This is not seeming very probable, is it? Well, hang on there. Let's wait a minute. Let's actually bother to calculate it. So this is going to come out to be about 2.3%. So it's actually 2.9 or 2.28%. 0.02 yeah, 228. Unless I'm much mistaken, a gives 10. Yeah, that works out. So, or about 2.3%, give or take, you know. All right, so there's a 2.23. So let's remember what we just figured out. So we said there's about a 2.3% chance that we're going to get a voltage measurement lower than 4.8 volts. Well, that doesn't sound very big until we remember that, wait a minute, this is a system. Remember my scenario was, what if we've got a sensor, we're reading a voltage from a sensor all day, every day in a manufacturing environment? We could measure hundreds of measurements in, I don't know, an hour, right? And what this says is over 2 out of every 100 measurements should give us a result that's below 4.8. So you could rely on this system faulting out a couple of times an hour. That's terrible. That's awful. That's completely unacceptable on a manufacturing floor, right? So this is actually, it doesn't seem like a big percentage. It's actually a problem. This is actually a problem that would need to be addressed. Okay, now let me just walk back through that really quick and make sure everything's clear. So, in summary, we started way back here. So, assuming you've got a you're monitoring noisy signal, we said there was a certain amount of standard deviation. We said there's a certain mean. So basically, we've completely defined a probability distribution function. We use the standard deviation and the mean to calculate a z-value for the voltage I'm interested in. We then constructed a condition. Skip over that. We constructed a condition. We said probability that the voltage is less than 4.8 volts. We turned that into a condition on z. We said, all right, probability that V is less than 4.8 volts. So what's the probability that Z is less than -2? All right, well, we didn't know how to calculate that with the table we had, so we had to do some magic to figure out how to construct that from the table we had. The truth is, it wasn't that hard. We just needed to know 2 facts. We needed to know that the Z tables are symmetrical. We needed to know that half of the probability distribution was a half. That shouldn't really seem that earth-shattering. And we needed to know that the whole thing was 1, right? We needed to know those facts, and from those facts we could figure it out, right? It's a little puzzle to figure out how to construct it, but it's totally doable. All right, well, thank you for your attention. I hope you enjoyed.